Now, can you give the devil's advocate from your perspective? Because from outside the profession, that seems whimsical. And, well, can you even reference these numbers? Are they literally like behind a veil that we can never even access that are out there? What is the justification for that kind of position?
Well, so the terminology that we use are computable numbers and uncomputable. So the algorithmic ones are the computable numbers, and the other ones are uncomputable. And the claim is that most numbers are uncomputable. Most in a very strong sense, in the sense that the measure of the computable numbers is 0, the measure of the uncomputable numbers is 1 in the interval from 0 to 1. So that's the claim. And yes, it's quite astounding. But I mean, most computer scientists would be very skeptical about that because, of course, they want to deal with algorithmic numbers, and they have no appreciation for the existence of so-called uncomputable numbers, which in fact don't figure in practice at all either. You know, and many people have said, well, why don't we just stick with computable numbers? Wouldn't that make life a lot easier? But it turns out that there's this thing called the axiom of choice, which is one of these set theoretical things that people like to believe in. And if you want to buy the axiom of choice, you basically are forced to buy all these uncomputable real numbers. They come as a package. So it's an unpleasant situation, and people kind of shrug their shoulders and say, well, let's just carry on.
Now, from my perspective, that position strikes me as eminently philosophic, in the sense that what it seems like the modern mathematical orthodoxy is claiming is that mathematical Platonism is true, that there exists these numbers that are out there that are inaccessible, incomputable, and I guess we can engage with them in some kind of limited fashion. But does that not require a very strict metaphysical claim that there exists these numbers that are out there separate of them being conceived?
I think you're absolutely right. I think that's correct. I think it is highly idealistic. I think it is highly philosophical. And in fact, in my view, 20th century mathematics really does have a strong philosophical foundation. I mean, the foundations of set theory and logic that were introduced in the early part of the 20th century really are coming from classical logic and the philosophical side of mathematics. And that's really dominated the thinking, at least in a sort of formal sense. It's like going to church once a year. You know, mathematicians will say they believe in this theory, but they say it just to keep people happy, and they don't actually really effectively use it. But it's a kind of it's a justification. It's a framework that will allow them to continue this belief in these real numbers, in these basically being able to complete infinite processes.
Okay, so let me ask you a couple short questions on this. When talking with people who have some kind of training in mathematics, or people who don't have training in mathematics, I actually was having a conversation with some engineers about this, and they said, Steve, how can you claim that there's no such thing as these completed infinities? Because in calculus, for example, we use completed infinities all the time. Central to calculus is this idea of the completed infinity, and they're conceiving of how limits work. So how do you respond to something like that, that if you don't have the completed infinity, well, you've just undercut a huge amount of mathematical thinking?
Well, yes, you do undercut a lot of current thinking, but this thinking has not always been this way. So in the course of the last 3 or 4 centuries, since the 17th century revolution, there has been quite a wide range of opinions and thoughts in this direction. So the current belief system is not really representative of the historical record. One has to appreciate that the way we think now is as a 20th century construction that would have been very alien to 19th, 18th, and 17th century mathematicians, even though it may be almost universal these days. But in earlier times, people did think about calculus problems and how to resolve them. They realized there were issues, and there was a lot of discussion, and I wouldn't say they were resolved entirely, but just prior to the 19th century, I think Euler and Lagrange were on a very positive direction. They had mapped out a direction that was leading to a more algebraic approach to things. And I think this is really where the potential for the future lies, is to go back to the Euler and Lagrange, who probably understood calculus better than anybody has before or since, and really build on their thinking. And it's possible to do that, and it's possible, I think, to go quite a long ways, but we need a kind of a more diverse pool of people thinking about, other ways of thinking, other alternatives to the limit-based orientation that we have now, which is basically a 19th century invention.
So do you think it would be a mistake to think that calculus can't work, or that there's no way of conceiving of an effective way of doing calculus without including the actual infinities?
Oh, absolutely. It's a very big mistake. In fact, I hope in my YouTube channel in the next year or two, to create a course on algebraic calculus and to demonstrate that, in fact, one can do calculus in a completely down-to-earth, cut-and-dried, write-downable fashion. So I hope to demonstrate this sort of directly, that these things are possible.
Okay, now what about something like geometry? Because at least from the outside, it seems like infinity also comes up in geometry. Is that something where you think, well, you really don't need any kind of infinities in geometry either?
Yeah, you don't need infinities in geometry. You can get around that. I mean, it's not that you don't want to talk about things, that one might say are infinite or infinitely far or something like that. It's just that you have to find a way of doing it in a finite, write-downable way. And people have wrestled with that in projective geometry. So in projective geometry, one introduces points which are at infinity, and formally that was considered rather mysterious. And what does it mean to have points that are infinitely far away, and so on. But the 19th century people like Mobius and Plucker understood really how to do this in a very concrete, beautiful way without any resorting to infinite processes. So one can do things. There are alternate ways of doing things that allow us to get at infinities, but in a finite, concrete, computable way. And let me add, right, that ultimately our computers, what our computers do is sort of almost by definition finite mathematics. So if you can get a computer to do something, it's almost necessarily based on ultimately finite thinking, because that's what a computer is.
Right.
And so computers are known to be very good at calculating lots of interesting things, and I think they're going to become increasingly important in the decades to come, even in terms of doing pure mathematics. And we're going to see that their limited, seemingly limited, non-infinity point of view will ultimately swamp our philosophical current approach.
So are there areas of mathematics which can't be rescued? If it's true that this idea of the completed infinity is a bit wonky, are there areas that really does fundamentally deflate?
Look, I think a lot of them deflate to a certain extent, but I wouldn't go so far to say they can't be rescued. I think every subject can be rescued and can be rebuilt and can be restructured and rethought. And I think there's a huge challenge that awaits 21st century mathematicians, is to really get down, roll up the sleeves, and really get down to the foundations and figure out how to do these things. So even modern set theory, I believe that what they're doing is not just out in left field, that there really is content there, but that they have to find some way of saying what that content is in a way that's concrete and finite and computable.
So from your perspective, this finitist perspective is very much in the minority, especially in the modern world. In my own discussions, in my own elementary understanding of mathematics, I get a lot of flack from people. I haven't produced nearly as much content as you have, just a fraction of a fraction, but I get a lot of flack from people who say, you can't get rid of infinities in modern math. I mean, you're just a crank. This has been settled 100 years ago. how do you respond to that? I mean, obviously, you're in the process of creating a ton of finitary mathematics that is very powerful and can be understood and without resorting to these grandiose stories and abstractions about infinity. Do you think that there is in the mathematics profession, do you think that there is a kind of, maybe dogmatism is too strong a word, do you think that there is an overconfidence, let's put it that way, in not establishing these foundational issues before going and doing their craft? So then one more concrete question that you can answer. Somebody who goes through the mathematics education and they get their PhD, right, they go through the system, are they going to be grounded in sound foundational reasoning about their subject matter? Or is that kind of overlooked to do the more interesting stuff? We just assume this is all correct, the foundational stuff, and then we do the interesting craft.
Sure, that's certainly true. Yeah, absolutely. I mean, the foundational problems are deep problems. There's a whole range of concepts which are not really spelt out clearly. You know, most of the elementary words in mathematics, from function to sequence to number to set, you know, these are just used loosely and kind of intuitively, and everyone kind of agrees that we kind of know what a function is, and so we don't really have to spend a lot of time and effort saying exactly what we're talking about.
Right.
And if we do say exactly what we're talking about, we tend to use the same or synonyms. You know, we play kind of a circular game. A function is a rule, and a rule is a process, and a process is a function, that kind of thing.
Right.
But, you know, look, I think that, sure, the modern PhD has been, you know, we are elements of our culture. I have been too. You know, we are taught along the lines of the current orthodoxy. It's important, and I think really great, and maybe you know your channel and your podcasts are doing this kind of thing, enlarging people's views of showing them possibilities that yes, there's an orthodoxy, but maybe it's not the whole story. In fact,
Right.
maybe it's not even the best part of the story. And certainly in my investigations in the last dozen years ago, so I developed this thing called rational trigonometry some 10, 12 years ago, and I've used that to reconfigure hyperbolic geometry. So I've discovered that, you know, this new point of view, I wouldn't call it finitist so much as concrete. You know, I don't really mind infinity if you can write it down in some concrete way. But this concrete approach really opens up so many beautiful new avenues for investigation. You know, the subject is so much richer to me now, having looked at these things with this concrete point of view. Because you have to appreciate that the foundational difficulties that are encoded in the imprecision of the way we use words means that a lot of mathematicians can't really get up close to the things that they're ostensibly studying. You know, like you can't really get a real number, for example. You can't actually possess an infinite decimal. So you end up saying things like, let alpha be a real number. Okay, that's different from let alpha be a decimal with eight digits.
Right.
That I can exhibit.
Right.
I can get right up close, and we can all have a look at it. But if you say let alpha be a real number, then there's a distance.
Right.
You know, and there's so many things in modern mathematics, more complicated, more sophisticated things that are of that kind, where there's a separation between the practitioners and the actual objects. There's like a curtain or a veil. You know. And getting rid of that, I think, really will bring so many things more into focus, that we can actually see what we're actually studying, and things will be more concrete, more precise. It'll be a completely different and I think more vivid mathematical world.
So you think that something like a real number, that this concept, absolutely elementary when conceiving about modern mathematics, you would make the claim that there is no actual clear, full conception of such a thing.
Absolutely. That's absolutely my position.
Well, I happen to agree with you.